We present an extension of level set-based implicit surface representations which can accommodate models with fine topological features such as narrow gaps and slits. We employ this framework to accelerate and simplify collision processing for volumetric elastic solids. Level sets define an object's boundary as a zero ISO contour of a signed distance function. Since this distance field is discretely sampled on a Cartesian grid, its resolution restricts how complex the interface can be within a single cell. Specifically, multiple interface crossings per edge cannot be represented. Instead of grids, we store distance fields in explicit meshes, which can have overlapping elements or topological bifurcation, providing a better approximation of the model topology. We record signed distance values on the nodes of such grids, and use trilinear interpolation within each cubic element to reconstruct the zero ISO contour, similar to standard grid-based level sets. We start with a stock embedding algorithm, which is the basis of our approach. First, we isolate the material contained within each cell. Regions with no material are discarded. We spawn a separate cell for each disconnected material component. Next, we examine all these disjoint cells and collapse faces of adjacent cells with material continuity. This process creates a connected mesh out of initially isolated elements. Once all cells have been processed, the resulting mesh can exhibit topological bifurcation as well as element overlap. We would now like to store signed distance values on the nodes of this newly constructed mesh. For most nodal locations, this is straightforward. However, extra attention is needed near elements with non-manifold connectivity. As we observe, such elements might disagree on whether their shared nodes are inside or outside the material. We reconcile this disparity by introducing special transition faces, which encapsulate the local connectivity between multiple connecting cells. In the paper, we provide further details on how transition faces are integrated into our data structure. Our work uses self-collision handling as the motivation of the non-manifold level set concept. We use non-manifold level sets to capture the rest configuration of a volumetric model, even when it contains thin features that would have rendered traditional level sets ineffective. We show how this can be leveraged to process self-collisions in difficult areas, such as the mouth region. Our next example is a volumetric elastic coil, with very narrow clearance between adjacent helices. Our non-manifold level set framework allows us to capture the boundary of this object without fusing nearby, yet disjoint, branches of material. Here we demonstrate user interaction with this model, while self-collision is being resolved. In this example, we disable self-collision and compress the coil into an intersecting configuration. Enabling self-collisions at this point allows for a very graceful transition into an untangled collision-free state, without necessitating a history of strictly collision-free states. Here we show an example of a surgical operation called a Z-plasty. Incisions in simulated tissues are difficult for traditional level set regimes to fully resolve. Our non-manifold level set is able to resolve the slit and allow for more natural-looking simulation with self-collisions. Self-collisions augmented with non-manifold level sets are easily combined with rigid body collisions utilizing traditional level sets. Here we demonstrate a woven net model which is stretched before a solid sphere is pressed into it. Our non-manifold grid generation algorithm can also handle mesh geometry inputs with zero-width cuts. Here we show a cube sliced down one axis with a grid pattern being collided against a sphere. Notice how both rigid body and self-collisions are correctly handled.